Yes, thank you, and good afternoon. My name is Rafael Grote. I have the honor to mainly present the work of Erin Thomas, who was working for the Norwegian Meteorological Institute until recently. She has sadly moved on and works now for the Los Alamos National Institute, if I'm not mistaken. She's still interested in the project, but has in the meanwhile other duties and other projects to attend to. And that I took over more or less where she left off. It's about a kilometer-scale coupled atmospheric wave and sea ice model. We're using again the AROME-Arctic model, but what was the motivation? So, as you have seen from the domain of AROME-Arctic in the previous presentations, that we cover a lot of ocean and as well areas with a lot of infrastructure in the Arctic, with communities on Svalbard and as well oil or fishing or tourism activities that of course are dependent on accurate weather forecasts to perform their operations safely. And in addition, the Arctic has some extreme weather events that propose quite some hazards, as for example high winds and large waves. Especially polar lows are one of those that impact the oceans, obviously, but as well the Norwegian coast, northern Norway. Those and together with colder outbreaks and vessel icing are typical situations that are dependent not only on the atmosphere but as well on the ocean and the waves. And with the changing in the sea ice extent, it's expected that those activities will increase in the future as well. So the importance of weather forecasts and as well more accurate forecasts that are taken into consideration the ocean as well are even more important. So here are just some examples of icing or severe icing on vessels at extreme waves, which can lead to quite dangerous situations. As an example of a polar low and what the challenges are with polar lows, we see one system here on the left as the satellite image, and on the right we have a bias of main sea level pressure and as well the mean absolute error, as well as for wind speed. And you see that this is displayed in with regards to distance from the polar low center, and you see that the closer we come to the polar low, the more will the bias and the error increase. That's probably because the scales of polar lows are quite small compared to synoptic systems, and they move quite rapidly. So errors in positioning and well as the intensity of itself, but the positioning itself can already lead to some very big errors. And in the forecasts, they have as well very sharp transitions between the high wind areas and the calmer areas. So with this in mind, the goal was to develop a forecasting system that improves short-range forecasts, and the idea was to couple wave and ice and atmosphere not only in a one-way direction, but in a two-way direction, so where the waves would actually feed back into the atmospheric model and therefore influence the wind again. Just an outline of the talk here that I'm giving. So I will shortly give an overview about the coupled setup. And then there was two forecast verifications done, one against land-based stations. Sadly, there's not too much of those stations in the AROME-Arctic area, since it's mostly ocean. And due to that, there was as well verification done against satellite altimeters and scatterometers. I come then to the conclusions of that work that was done by Erin and published by her, and then talk a bit about how I continued with the model. It's less about the performance of the model itself, but a bit more of how this performed in an operational setting and what the future outlook of such a coupled model might look like. So, as said, we used the AROME-Arctic forecasting system with a 2.5 kilometer grid, and The wave model used was WaveWatch III, and we used an OASIS 3 coupler. And in addition, it had the sea ice model from Yuri Batrak, which in this setup had mainly the function of dampening the waves as soon as they reach the ice. The general concept behind this is that we have the wind that is influencing the waves, and the waves, of course, change the roughness length of the surface and thereby feed back into the wind and introduce a stress that might change the wind again. And yeah, the model was run then in a period between December 2019 and January 2020, and it was once done in a one-way coupled way where only the wind influenced the waves, but not the other way around, and then in a fully coupled where both waves influence wind and the other way. It was done for 48-hour forecasts, initialized every 12 hours. There was 3-hour coupling, but only those every 12-hour runs were of the full length. And yeah, the stepping of the models were that we had the standard stepping of 1 minute for the atmospheric model, and the wave was run with a 5 minutes time step, and coupling took place every 30 minutes. Although it was then, for the coupling, it was always, so the wave model was lagging 5 minutes behind because the information used from the waves was from the previous time step. This is an example of one weather situation during that period with a low pressure system with high winds and high waves. And you can see here the wind speed of the coupled model on the left and the significant wave height of the coupled model on the right. So this is now the verification against the stations, the observation stations. So this is, you see on the left side those 3 spots. That one is on Lofoten, the red one. Then we have Bjørnøya in green and Jan Mayen in blue. And on the right side you see surface pressure and wind speeds. So the solid line is the observations, and dotted and dashed are uncoupled and coupled respectively. And you see they follow along and are quite similar, but there is some differences between those models as well. If you look at that in a more, looking at the statistics of this, you see that there's actually a decrease in all error metrics, that is bias and mean absolute error, as well as standard deviation for all of the 3 locations. So there was an improvement visible for all places there. Obviously, it's only 3 stations, so it's hard to know what happens on the ocean. The next thing was then verification against satellite data, and we and Erin used here those correspondence thing to calculate the standard deviation, mean absolute error, and bias as well, and did then from those correlations go on to calculate it for each of the forecast hours from 0 to 48 to see how those evolve over time. And we could see that the correlation was more or less stayed constant, with except for 10 winter wind speeds for the small for the first forecast hours, where the correlation of the coupled system actually decreased. Correlation for significant wave height increased over the whole forecast time. I will talk about this if there's time a bit later. If we look at the standard errors, standard deviation of the errors, you can see that there was an improvement from uncoupled to coupled over the whole length of the forecasts, especially for significant wave height. There was a real improvement. And yeah, looking at again at the statistics, you could see the improvement was mostly for high wind speed situations and high wave situations, while there was some worsening of the performance for small wind speeds and smaller wave heights. So to conclude, there was an increase in the error statistics of mean absolute error, bias, and estimated standard deviation for all 3 locations. and as well for high wind speed situations and high wave situations of when comparing to the satellite data. So in general, there was a good agreement between a coupled model and satellite-based observations, and at least not a worsening of the model. So there is some improvement that can be felt from having a fully coupled system. So that is good news in itself. But then we went over to see how this system can work in an operational setting. And the design was in the beginning to run for 1 month in the spring of 2022, so this year. And we wanted to have a fully coupled run similar to the one that Erin used in her experiments. There was, we couldn't really, or I couldn't really focus that much on scientific results, because there was some, the main results of that experiment was to actually get the model running in an operational setup. Erin used it in a scientific setup, and the AROME-Arctic or the HARMONIE models are a slightly different setup when it comes to operations and scientific setup. So there are some switches and some scripts that need to be adapted, and to find out where those problems lie and what needs to be improved was actually then the main outcome instead of any scientific results. But we could get an estimate of the running costs, and as well find out where there's more problems that need to be solved. So just to show you here, this is an estimate. This is not exact numbers, but it gives an indication. In blue, you see here the runtime for only the forecast step, not all the preparation that takes place with achieving boundary data or post-processing, but this is really just forecasting. And in blue for the coupled system, and in red for the operational systems that run on a routinely, the everyday routine for AROME-Arctic. The dots give you an indication of how many nodes were used on the supercomputers. They were more or less similar. We used a bit less for the coupled system, but not much. But you see as well that it took twice as much time to run the coupled system or a fully coupled system compared to the uncoupled system, which of course is nothing that can be done in an operational setup now. It was a bit disappointing, and we don't quite understand now why this happens. There was some improvement done to the wave model before, which should have improved runtime by 30%, but we didn't see that come through in those experiments in the end. So there must be a bottleneck somewhere in the system that we haven't been able to identify. In addition to that, we might need to experiment with node setups as well that were not really, Erin hadn't done any work into that because it was not part of the research that she did. Yeah, and with that, I want to thank you, and I don't know if there's time for a few questions.
So, one quick question.
What kind of coverage does the ASCAT have near the ice edge? Was the effective validation that you did with ASCAT effectively open ocean, or was it?
It is open ocean, and the verification was only taking place where we have actually a passing. So it was not compared against the whole model. It was really just taking the cases where we have a satellite pass, and only for those times where the satellite were passing as well. So it's an excerpt, not the complete results of the model that were used for that.
So not much validation. Not much validation then near the in terms of the effect of the ice coupling then.
No, it's mainly it was only the ocean, and yeah, I think the reasoning behind that was since it is a wave model and the waves getting damped, it's more or less that where you expect the most effect of the waves.
Okay, I think we should